Now moving into unit number 2, and this is density, the atomic theory, and nuclear chemistry. So first of all, density is defined as mass per unit volume. Again, D over or D equals M over V. The symbol for density is capital D, or the Greek letter rho, which is a P that looks like the Phillies P from baseball. So density is mass over volume. Now common density units, when we're talking about the English system, for pounds or for solids and liquids, you're looking at pounds per feet cubed. As for the metric system, we'll use grams per centimeters cubed. The SI, or Systems International Unit, accepted unit internationally, is kilograms per meters cubed. Doesn't always make much sense because we don't use that really in the laboratory. It's a larger amount. For gases, we're going to find we'll actually use grams per liter when we deal with the density of a gas. So the big part is we've solved for density, and we're going to practice solving for density, but we're going to also be able to use density in that of dimensional analysis. So we saw some problems here going from density of gold, 19.3 grams per centimeters cubed, and just kind of going through straight up dimensional analysis, changing from one unit to another unit, from a grams to kilograms, visual metric to metric. Then we go from centimeters to meters, and then we have to cube that conversion factor. Remember that when you have an exponent being raised to a power, you just multiply it. So 10 to the negative 2 raised to the power of 3 is actually the value of 10 to the negative 6. We go through these values again, grams per mil, grams per centimeters cubed, they're the same thing, so you don't have to do any math. For pounds per feet cubed, I'll change my grams, and this is my centimeters to inches and inches to feet. We cube both those conversion factors, and I'll just change from grams to pounds, and we have a conversion factor for that. So we see this 19.3 times 2.54 cubed times 12 cubed divided by 453.6 equals, and so we've actually done this before. So feel comfortable about it. This is just straight up dimensional analysis using density. Well, another term that's going to come into play is also called specific gravity. And when we're actually working with specific gravity, what specific gravity is the density of an object divided by the density of water. Well, density is a mass, grams per centimeters cubed, divided by the density of water, which is grams per centimeters cubed. We see that the units actually cancel out. So we're going to find out specific gravity has no units to it. So again, we're going to find out, since the density of water within room temperature is 1 gram per mil, or 1 gram per centimeters cubed, the units will cancel out, but you're dividing by 1, so numerically, specific gravity and density are the same. For example, if I know that gold has a density of 19.3 grams per mil, if I calculate specific gravity, just take units off, and because it's grams, density of my gold divided by density of water, the units cancel, divided by 1 is still 19.3. So specific gravity is numerically the same as density, just no units. Units on, density, units off, specific gravity. Okay, now specific gravity has the same value in any system of units, since it expresses a quotient of the mass of a substance divided by the mass of the equal volume of water. It is expressed by a pure number without units. Again, units off, specific gravity, units on, we have density. And is usually used for liquids. And again, we have this numerically the same because within room temperature, the density of water will remain the same at 1 gram per mil. Now, in actually calculating density, and you're going to be doing this actually in lab as well, you'll find we know there's two variables within density, and it's mass and volume. The mass is going to be easy because it's always just using our balance. However, the volume is where we're going to kind of play around with the different techniques of actually going after volume, one of them being just water displacement. But first of all, let's say we have a geometric shape. And so we have a rectangle here. We can measure its length, width, and height. And that will give me my volume. And then I take the mass acquired from the balance. And actually, I can plug this in. We actually did this in class. So as an example of ours, I had you measure the block. We got the mass of the block. And we did mass divided by my volume, which is length times width times height. And so mass divided by length divided by width divided by height equals. And so we got the density of this block. Also, another technique we use, and this for irregular shapes, is called water displacement. And so water displacement, again, is the water literally gets displaced by the volume of the object. So the increase in volume is due to the volume of the object. So to calculate our volume, we would put VF minus VI, and this is your V final minus your V initial. So your initial volume subtracted from your final volume. The only difference in this volume is the volume of the actual shape. So again, you get this mass based upon with your digital balance. Again, mass divided by my volume of the object, which is VF minus VI, and you get density. Now we go through some density calculations. Again, density calculations. First, number one, we see an object with a mass of 1 kilogram and a density of 4 grams per mil. What is the volume in liters? So first of all, my density is a mass, and the density is in grams. My mass of the object is in kilograms. So first, initially, I need to change it to grams to match up with my density. So kilo to the third, I'm going to move 3 places back to the right. So 1 kilogram is the same as 1,000 grams. I have my density. Another thing I would like to encourage you to do, once again, is take your density equation and solve for your unknown variable, which is volume. So you're going to, in this situation, just volume and density trade places. So mass divided by density is my solve that equation. Again, I can muddy it up with numbers. Then I take plug my mass of 1,000 grams, plug my density, my unit grams are going to cancel out, and end up in milliliters. But I didn't want it in milliliters, I wanted it in liters. So now I move it 3 places back to the left. And we'll maintain 3 sig figs in this situation because both are my original mass is 1.00 kilograms, so that's 3 sig figs. Again, we don't look at density for significance. Number 2 says, what is the mass of a 500 gram object that has a specific gravity of 0.800? Remember, units on, density, units off, specific gravity. So I just have to put units on. I'm going to use grams per mil or grams per centimeters cubed. Those are my 2 default. Since my volume is already in centimeters cubed, I'm going to use just grams per centimeters cubed. So I have my density and I have my volume. You know, I isolate mass, so I can just multiply both sides by volume. So in this situation, we have 500 times 0.800, and centimeters cubed cancel out and end up in grams. So I have 400 grams. Again, because the ambiguity here in my original value, I could have anywhere from 1 to 3 sig figs. My 500, don't know. This is why in this situation I would accept either 1 to 3 as well. So for example, you could put it in scientific notation as you need to. The next one, number 3, it says an object has a density of 7.2 grams per milliliters. When we know specific gravity, we'll just take the units off. And we see units on, density, units off, specific gravity. Number 4, what is the density in grams per centimeters cubed of solid gram cylinder that has the 4.00 centimeters tall and 2 centimeters wide? So in this situation, your wide means your diameter. We know the mass. We need its volume. So it's going to be it's a cylinder, so volume equals pi r squared h, where you have your h is 4 centimeters, your height, take half that or your diameter, excuse me, at 2 centimeters, take half that is 1. So you can actually solve for the actual volume. We can carry out substitution here if you wanted to, in the substitution. So I have my diameter, I have my height. And so again, this is all the process of taking what you know, the Google Map technique. We identify what we know here. So I'm going to isolate, just change out my volume with pi r squared h, and I want to solve for the density so I don't have to manipulate the equation. I'm just going to plug my mass at 75.84, divide by pi, divide by my radius, which is 1. 1 squared is still 1, and divide by my height, so I'll divide by 4. In this situation, my density comes out to being 6.04 grams per centimeters cubed. Now look at my original values. My mass had 4 sig figs, but both my diameter and the height had 3 sig figs. Therefore, my answer has 3 sig figs. The next one says calculate the diameter of a 16-pound shot put. And it says a shot put, again, just explaining that the solid metal ball thrown with track athletes, and has a specific gravity of 7.78. Calculate the diameter in inches. So I want to know the diameter. So what you realize here, you realize you have mass and you have density. With mass and density, I can solve for volume. And then I'm working with a sphere, so I know volume equals pi r 4/3 pi r cubed. So it allows me to isolate my r. And once I have my r isolated, just double it, multiply by 2, and that's my diameter. My whole thing is, first of all, to use my density, which is 7.78. I can use grams per mil or grams per centimeters cubed. And then my pounds, my shot puts in pounds. So first of all, I have to do is match up my pounds to grams, and we know that because we can do that, but we know 1 pound equals 453.6 grams. So we can actually convert that over. Here's just again a good picture of it all, identifying what we know. We have a 16 pounds. We know our conversion factor for pounds. We get that. We make the conversion over mass to grams. Specific gravity, which is we know numerically the same as density. We know you're dealing with the volume of a sphere. We know density equals mass divided by volume. We substitute in place of the volume in our density equation, 4/3 pi r cubed. We for our density, we just for our diameter, it's a d over 2, and we could go through a whole substitution here if you wanted to, but you don't need to. The easiest way is just isolate your r and then multiply by 2, and that's how you get your diameter. So again, we've done this before. Get rid of our 4/3 by get rid of our fraction or our denominator by multiplying through by its reciprocal. We then trade radius, cube, and diameter can trade places, and we take the cube root of both sides. Then we just plug in our mass, we plug in our density, and do the simple math. 3 times the mass divided by 4 divided by pi divided by my 7.78 equals, and you take the cube root of that, and you have your radius at 6.06 centimeters. Just double that, and it gives you now the diameter. And going from centimeters to inches, we know that there are 2.54 centimeters in an inch, so you're going to divide by 2.54, and you actually get your diameter and inches. Again, 3 sig figs, going back up to my original value, I'm not going to look at specific gravity, universally accepted. I will look at my 16.0 pounds, so it's 3 sig figs, therefore my answer has 3 sig figs.